octet rule.
What up? Oh, wait.
8. Octet rule. Chemical bonding. We're going to hit you up with a learning target, which is
Coming your way.
you got to explain why atoms will react to form chemical bonds in compounds invoking the octet rule. Why does hydrogen bond with chlorine? Well, because when they do, both of them have a full octet.
Right.
Etc.
Or do it. And then the other thing you're going to need to be able to do is explain the relationships between energy. Do I have to put energy in to break bonds, or do I get energy out when I break bonds? You got to understand which way we're going.
Right. Cool. There we are. So why atoms form bonds in the first place? Well, these atoms want to gain or lose their valence electrons in order to get a stable electron shell. And that stable electron shell has a magic number of 8. For some reason, I don't know, I can't read the mind of God, why he made up 8 was like just what's up. 8 seems to be the stablest configuration.
Yep.
So for most atoms, 8 electrons in the exterior shell, the valence shell, makes it stable. Hydrogen and helium are the exceptions because these two elements only have room for 2 electrons in their outside shell. But it's still filled when there's 2. So that is just as stable as having 8.
There you go. Mm-hmm. And in the picture, we're seeing that you see that fluorine -1 ion has gotten that 8th electron to fill its outer shell in that Bohr diagram. Okay. And so in ionic bonding, we're going to deal with a metal atom completely transferring its valence electrons, because remember, metals are losers. They want to get rid of their electrons. They're going to completely transfer their electrons to the nonmetals, leaving both now with stable valence shells. Mm-hmm. Okay, so the 8 that's underneath in the kernel for the metal is now stable because it lost that 1 or that 2 that it had. And in this case, the fluorine in the picture scooped up 1 from one of these metals.
The inner ring of 2 is already mad stable.
Correct.
But the outer ring is not stable, and the whole atom wants to be stable. So it's got to fill up that outer ring. And for fluorine, it's easier to find 1 more electron
than to lose 7.
Yeah. Okay. So for some examples.
Ooh, you got some drawing to do.
I do. Yes, you do.
Yeah, you do.
We do want you to draw the Bohr models and the bonding.
Yes. And
of
it
this,
really does
exactly the way you
what's
see
going on, because as you see, this electron from the sodium, the metal, loses and goes over to the Cl. Complete transfer. And now this plus and this minus, whoop, they form that connection like magnets.
Yeah, absolutely. Opposites attract. Okay, so the positive charge and the negative charge will get locked in a ratio 1 to 1. So the chemical formula for salt, NaCl, table salt, sodium chloride, is NaCl because of that ratio of positive to negative charges in the ions that are formed through the complete transfer of an electron.
Right. Exact same thing's happening here, except for calcium has 2 electrons to give, and chlorine only wants 1 each. So notice 1 goes to 1, 1 goes to the other. But I have a calcium +2 ion. Now I need 2 chlorine -1 ions to cancel out, because +2 -1, those don't jive.
Right.
So I need 2 -1s. And the picture illustrates perfectly what we're talking about. Right. And while we're here, you could see the notation would be up top CaCl2. What that 2 mean?
That means there's 2 chlorines for every calcium, which you can kind of see in the picture of the Bohr models as well. 1 calcium atom on the left, 1 calcium ion on the right. 2 chlorine atoms on the left, 2 chlorine ions on the right.
Yep, there you go. So
that's it. That's what subscripts mean. Yep. The number of atoms that are preceding the subscript.
Yeah, that's the thing that we don't want you to get confused about. It's the element before the subscript that the subscript's talking about. Right. So we got to make sure we got that.
Now, some examples, it's easier to use atoms, brackets, charges, and dots to show instead of Bohr models, especially when your atoms get too big. Deeper in the periodic table, add mad many electron shells. I don't want to draw all them kernels, so I'm going to use the Lewis model to show it simpler.
Yes.
So CaCO3, what do we got for us?
Well, it's a Ca with a +2, and CO3 has a -2, so I need 1 of each.
Yep.
And we're actually going to learn a way to do it without drawing that structure for the CO3. And we haven't given you any instructions yet on how to draw these things. So why don't you just get a feel for what's going on before we give you all the rules.
This is how I would draw it without the bonding. It would be literally Ca, +2.
Yep. And then just do CO3. Yeah. With a -2. Done. Beautiful. As a matter of fact, we're going to do that again right now with the NaSO4. The only problem here is that we have to draw the Na twice because there's two of them.
Do I actually get to draw this time?
Yeah, yeah. You get to draw some. Yeah, buddy. So we're going to do the Na, and the Na, you got to draw it twice. They both have a positive charge from the periodic table.
Twice.
+1.
Why is it twice, Mr. Milks?
Because that 2 at the end of that Na2 means there's
two
two
NAs. Preceding element, you get 2 of them.
Right. So here I'm going to draw both. I'm going to put a bracket around them because we're going to find later what these brackets mean. But what they mean is my electrons, you cannot have them. And then there's one SO4. That's a polyatomic ion. When in doubt, check E out. We're just going to keep that together. The 4 is talking about just the oxygen, not 4 SOs.
Now we got to invoke a little math logic.
Ooh, here we go.
If there's 2 Na positive ones,
+1 and +1 is.
+2.
So what do you think the charge is on the
SO4? Well, it's going to be opposite, so it's going to be a negative.
Yep.
And there's only one SO4 and it cancels out. So I'm going to say it's -2.
I think you're right. And on table E in our reference table, you're going to find SO4 is sulfate, and the only discrepancy there is that it's going to say 2-.
Yeah.
So we're not going to get hung up on that. That's a New York State thing that Monaco and Milks didn't do, but just so you can see, ready? SO4 is here somewhere. Oh, there he is. See, SO4 with a -2 charge. Says 2-, but we'll call that a -2 between brackets.
Means the same thing. Yeah. It really does.
And now these octets are stable. And
That's
let me do covalent quick.
Cool.
Sweet.
Yeah.
So covalent, we're going to have 2 nonmetals now by rule that share their valence electrons and leaving both now with valence shells. Again, we haven't gone through all the rules of drawing these yet, but we're just going to draw them up
preview
a little bit so you can see them. Do you want to draw them with just their lone electrons first?
Sure.
So H2 means that there are 2 hydrogens. Each one has 1 valence electron. I'm going to form that bond. So when I put them together, each hydrogen wants 2. So if they share, they'll both have 2, and there's them sharing. And we're going to learn to redraw that sharing of 2 electrons. If you connect the dots with a line, you get a bond like in the bottom picture. And we're going to get it right now. Ready? HH. Now that bond means 2 electrons, one from one H, one from the other, and we showed you how to get there.
Yep.
Cool.
We converted the 2 to 1 line. That's it.
That's it. We have 2 more quick examples following the same protocol. We have HCl, so I have 1 H and 1 Cl. The difference here is Cl has 7 valence electrons. He only wants the 1. So if they share right through that plus, they share, then everybody will have their octets filled. See, you're getting the hang of this. You could almost, after watching him do this, come up with the rules of how to draw these, I bet. We don't even probably got to give you rules, but we're going to anyways.
Are those 6 electrons necessary on chlorine?
Yes, very much so.
Because those are the 6 that are not involved in the chemical bond.
Yeah, we call each 2 pairs a lone pair. And if you notice, if you were to put a circle around that chlorine with the bond, all the electrons are on one side now.
Yep.
So that gives me that negative on one side with a positive on the other side. And that's going to come into play later on in the unit.
Polar molecule.
All right, we got to get through H2O kind of quick.
Okay.
So I got 2 H's and I got 1 O. So this is just like a puzzle, if you will. The O needs 2. So a hydrogen is going to give 1 to one set, and the other hydrogen is going to give 1 to the other. And this is a lot like putting together a puzzle. And you will see, there we go. We can redraw it now with our bonds. Just don't forget to put in those lone electrons, and you will have the actual picture of water. And it does have that bent shape, and that is what it's going to look like final product. Notice 8 electrons around oxygen. If you count each bond with 2 electrons, each hydrogen will have 2, and they're happy, and we good.
Yeah. Is that it? Metallic bonding.
Yep. So here is that sea of electrons that we didn't get through very good last unit, but we had to talk about it a little bit. And the picture shows you that the electrons are free to move around. And then real quick, atoms get to a lower energy when we bond. So the energy is given off.
Yep.
And when I break a bond, just like you think of breaking, you got to add energy to get it to break.
Yeah. Absolutely, sir.